Hey, today's topic, a very brief introduction to differential equations. What is a differential equation? Well, it's simply an equation that involves an unknown function and its derivatives. Here we have an example. 2 times some function y is equal to x times the derivative of that function y. This is a differential equation. And the solution to a differential equation is the set of all functions y that make the equation true. So for the example that we're looking at here, 2y equals x times dy dx, it's not hard to show that the function y equals e to the x is not a solution. And we can check by plugging in the function y equals e to the x into that differential equation. And we would get that 2 times e to the x equals x times e to the x. Now that might be true for some particular value of x, but it's not true in general. And so this function y equals e to the x, not a solution. On the other hand, we can also check that y equals x squared is a solution to this differential equation. And we do it the same way. We plug in the function y equals x squared. And we find that 2x squared is equal to x times 2x, which is certainly true, telling us that y equals x squared is a solution to the differential equation. And if we're given a differential equation, there are 3 interesting questions. The first, is there a solution to the differential equation? The second, if there is a solution, is there more than one solution? And the last, if there are solutions, how do we find them? And it turns out that the first question, is there a solution, is really hard. We're going to ignore it altogether and focus on the second 2 questions, and we will only be looking at differential equations that we can solve. Let's look at a simple example. This differential equation, dy dx equals x plus e to the x. The trick is to essentially multiply both sides of this equation by dx. Now, can you really do that? I mean, dy dx is something that means the derivative of y with respect to x. It's sort of a symbol for the derivative. Can you really split it in half as if it were a fraction like that? And it turns out that the answer is yes. The symbol is very carefully chosen so that this kind of manipulation of the notation works. And the beauty here is that on the left-hand side of the equal sign, we have something in terms of y. On the right-hand side of the equal sign, everything is in terms of x. And so we can integrate both sides. And this turns out to be a very simple integral. We get that y is equal to 1/2 x squared plus e to the x plus a constant. You could worry about the constant when you integrate dy. Technically, you have y plus a constant is 1/2 x squared plus e to the x plus some other constant, but then subtract the constants from each other and you just get a single constant, and so we may as well just leave it there on one side of the equal sign. What you can't do is forget the constant. It's going to be very important, and those of you who tack it on at the end are going to be burned very badly in this study of differential equations. So don't forget your plus c's. It's easy to check that the function we came up with here really is a solution to this differential equation. You simply take the derivative of both sides and you get dy dx equals x plus e to the x. So it very obviously solves the differential equation. In particular, our solution to this differential equation is this infinite family of functions, y equals 1/2 x squared plus e to the x plus a constant. In other words, for every different constant, you have a different function. And so this is what we call the general solution to the differential equation. And we have pretty much answered the second of our 3 questions. If there is a solution, then there will be infinitely many of them. An infinite family of solutions to any differential equation that we can solve. Okay, the example we just looked at is a special case of a type of differential equation known as a separable differential equation. It's separable if you can write it as dy dx is some function of x divided by some function of y. And how do we solve such a differential equation? Well, you multiply both sides by dx, you multiply both sides by g of y, and then you integrate. You get everything with the y's on one side, everything with the x's on the other side, and then you take the integrals of both sides and go from there. That will give the general solution to a separable differential equation. And just a quick note, the word separable comes from the idea that we can separate the variables this way. It is algebraically possible to get everything with the y's on one side of the equal sign and everything with the x's on the other side of the equal sign. That won't always be the case, in which case the differential equation is not separable and you'd need other techniques to solve it. Okay, let's look at this differential equation. dy dx equals x squared times y. And if you multiply both sides by dx and divide both sides by y, you get 1 over y dy equals x squared dx. So we've just separated the variables, which lets us integrate both sides. And on the left, we get the natural log of the absolute value of y, and on the right, we get 1/3 x cubed plus a constant. Now, it's not always possible to solve for y in a differential equation, but in this case it is, and so when it is possible, it certainly makes a nice, tidy answer if you can write y equals something or other as your solution, which we will do. And to deal with the unfortunate problem that the y is wrapped up inside a natural log, what we do is we raise e to both sides, because e to the natural log of anything is just the anything. They're inverse functions. And so we get that the absolute value of y is e to the 1/3 x cubed plus a constant, which is certainly better than what we had before, but we're still not done. And this next technique shows up quite frequently in solving differential equations, so pay close attention and make sure that you get it. The idea will be to take the expression on the right and use the properties of exponents to rewrite it as e to the 1/3 x cubed times e to the c. You're not used to going that way, but if you had seen e to the 1/3 x cubed times e to the c, you might know that the exponents add in that situation, giving you the line that we had before, e to the 1/3 x cubed plus c. Well, it works the other way as well. If we have e to the 1/3 x cubed plus c, we can split it up into e to the 1/3 x cubed times e to the c. And the beauty here is that e to the c, well, c is some constant, e is a number, e to the c is just some different constant. And so we can rewrite this as absolute value of y is equal to some constant times e to the 1/3 x cubed. It's not the same constant that we had a moment ago, and if it makes you more comfortable, you can call one c1 and the next one c2 or something like that, but they're both just constants. And aside from perhaps looking a little bit cleaner, how does that help? Well, I'd love to get rid of the absolute values around the y, and so I'll consider separately the cases where y is positive and y is negative. And if y is positive or even 0, then the absolute value of y is just y, and we get that y is c times e to the 1/3 x cubed. On the other hand, if y is negative, then the absolute value of y is negative y. For example, y is -7. The absolute value of -7 is -7. That gives us +7. And so we get negative y is equal to c e to the 1/3 x cubed. And if you multiply both sides of that equation by -1, you get that y is equal to c e to the 1/3 x cubed for a different constant c, the negative of the one that you had there before, but it's still just a constant. And so what we found is that whether y was positive or negative, we got the same expression, c e to the 1/3 x cubed. And that lets us write our answer simply as y equals c e to the 1/3 x cubed, since that's what it's equal to for all possible values, positive or negative or 0 for y. And so we have a single answer, y equals c e to the 1/3 x cubed, the solution to this differential equation. And if you had the time and you wanted to, you could certainly check. You'd take the derivative and see that it was equal to x squared times this function. Okay, you try this one. See if you can solve this differential equation. dy dx equals x e to the negative y. It'll help to remember what e to the negative y means. E to the negative y, the same thing as 1 over e to the y. So take a moment. See if you can work this out. Pause the video. When you're ready, start it back up. Multiplying both sides by e to the y and multiplying both sides by dx gives us this expression here, e to the y dy equals x dx. And you can see that either by thinking of e to the negative y as 1 over e to the y, so that when you multiply it by e to the y you get 1, Or you can just look at the properties of exponents, e to the negative y times e to the y. The exponents add, and you get e to the negative y plus y, which is e to the 0, which is 1. And however you look at it, we're now ready to take the integral of both sides. And we get that e to the y is 1/2 x squared plus a constant. I'd like to get the y out of the exponent. To do that, you have to take the natural log of both sides. You have to be a little bit careful. You're taking the natural log of the entire left-hand side and the entire right-hand side. The idea being that if these two things are equal, then their natural logs are equal. And the natural log of e to the y is just y. And that gives us our answer. Y is the natural log of 1/2 x squared plus a constant. This is the general solution to the differential equation. Sometimes, even often, you're asked for a particular solution where you're given more information, as in solve the differential equation dy dx equals x e to the negative y, such that y equals 5 when x equals 0. And there are other ways to word this. Sometimes it's written as passing through the point 0, 5. That means when x is 0, y is 5. Or occasionally it will be written like this, such that y of 0 equals 5, with the idea that y is a function of x, and so 0 is the x value there, and the y value that comes out is 5. In any case, instead of the infinite family of solutions here, we're looking for a particular one that satisfies this condition. How do we find that? Well, we plug in x equals 0 and y equals 5, and solve for the value of c that will make that true. In other words, take y equals the natural log of 1/2 x squared plus c, plug in y equals 5, plug in x equals 0. And since 0 squared is 0 and 1/2 times 0 is 0, this gives us that 5 is the natural log of c. And raising e to both sides, we get e to the 5th is equal to e to the natural log of c, which we do because e to the natural log of c is just c. And so we just determined that c is e to the 5th. And so the particular solution to this differential equation that satisfies this initial value, this idea that when x is 0, y is 5, is this function here, y equals the natural log of 1/2 x squared plus e to the 5th. And this is called an initial value problem, where you're given a differential equation to solve and given some initial value so that you find a particular solution, not just the general solution. Okay, see if you can do this one. Find the solution to xy dy dx equals 1, such that y equals 3 when x equals 1. Pause the video, take a couple of minutes, and when you're ready, start it back up. The first step is to separate the variables, divide both sides by x, multiply both sides by dx to get y times dy is 1 over x dx. And then you can integrate both sides. The integral of y times dy is the integral of 1 over x dx. These are easy integrals. Don't forget your plus c. And we'd like to know what y is equal to, so we can start by multiplying both sides by 2. That gives us that y squared is twice the natural log of the absolute value of x plus 2 times c, which is just a different constant c, so I'm still calling it c. It doesn't make sense to write 2c because that's just another constant. But if you like, if it makes you more comfortable, call the first one c1 and the next one c2 so that you can keep in mind that you have changed constants there. Not necessary, but if it helps you, then do it. And so the general solution to this differential equation is y is equal to the positive or negative square root of twice the natural log of the absolute value of x plus a constant. If we're looking for the particular solution that has y equal to 3 when x is equal to 1. And so we plug y equals 3 and x equals 1 into our results. Now 3 is never going to be the negative square root of something. 3 is a positive number, and so it's the positive square root of something, and so we can lose that sort of annoying positive and negative. And we get that 3 is the square root of twice the natural log of the absolute value of 1 plus a constant. The absolute value of 1 is 1, and the natural log of 1 is 0, and 2 times 0 is 0. And so this simplifies to 3 is equal to the square root of c. We'd like to know what c is, so we square both sides to get that c is equal to 9. And so our final answer, the particular solution we're looking for, is that y is equal to the square root of twice the natural log of the absolute value of x plus 9. And notice that I can still keep the positive negative out of this square root. I'm only looking for the positive square root because if I also included the negative square root, then when x was equal to 1, y would be both positive 3 and negative 3. And I want y to be positive 3. That's the initial condition that I was given. And so this is the answer. Okay, that was the briefest of introductions to differential equations. You should be in good shape to start your homework. You should be in good shape to finish your homework. Give your homework a try, have some fun with it, and I look forward to seeing you in class. Bye.